Welcome to another mathologer video. See that infinite series up there? 1 minus 1/2 plus 1/3 minus 1/4 and so on. So the terms are the reciprocals of 1, 2, 3 and so on, and the signs plus and minus take turns. Look familiar? Well, that's the famous alternating harmonic series, which quite a few of you will have encountered before. For example, in some of my older videos. Recently, I stumbled across a new, extremely beautiful visual resolution of a very nice and very important paradox that arises from this infinite series. And so this is what I'll show you in the first part of this video, before heading down the crazy rabbit hole opened up by this nice new discovery in the second part. As usual, I've got lots of great aha moments lined up for you that you won't find anywhere else. Enjoy! Okay, so first, where is that paradox hiding? Well, here we go. Let's focus on one of the negative even denominator terms, say minus 1/6. Let's rewrite minus 1/6 as 1/6 minus 2/6, right? Minus 1/6 minus 2/6, that's minus 1/6. Okay, now 2/6 simplifies to 1/3. Do the same for minus 1/8, so that minus 1/8 equals 1/8 minus 2/8. And 2/8 simplifies to 1/4. Nice pattern there. So let's do the same for all the other negative even denominator terms and substitute like this. There, 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 and so on. Forever and ever after. Okay, so that's another way of expressing our original sum. Here comes the punchline. Ready for a surprise? Separate out the positive and negative terms. Look. Every term at the top is cancelled out by a term at the bottom. How nice is that? And so what's the sum? Well, since everything cancels, the overall sum must be 0, of course. Except it's not. Starting with 1, adding more and more terms, it turns out that the finite sums we come across in the process never dip below 1/2. In fact, on closer inspection, these finite sums get closer and closer to a special positive number. And this special positive number turns out to be the natural logarithm of 2, which is approximately equal to 0.7. So, that's our paradox. Although every positive term is cancelled out by a negative term, the official, mathematically sanctioned, term-by-term sum of this infinite series is different from 0. So, what's the explanation for this nice paradox? Well, let's have a close look. Anything that sticks out to you? Of course, there, 314. The answer is pi, 3.14. Well, no, not at all. The digits 314 showing up here is really just a freak coincidence. Well, did I manage to trick you there for a second? No, what's really important here is that in our infinite series, there's this imbalance between positive and negative. There's always 2 positive terms followed by 1 negative term. And so, while every positive term is really eventually cancelled out by a negative as we keep adding, the imbalance approaches this special positive number over there. But you don't have to take my word for this. What I'll show you next is this new spectacular way of visualizing how this imbalance evolves and that it really approaches the natural logarithm of 2. Alright, let's sum this monster visually. I'll just put the brackets back in to remind us where all this comes from. Now, all those terms, 1, 1/2, 1/3 and so on, can be nicely pictured using the familiar 1 over x graph, right? At x is equal to 1, 1 over x has the value 1. And then this square here also has area 1. What's the area of this rectangle? Well, 1 unit wide and 1/2 high, and so its area is 1/2. Then we get 1/3 as the area of this rectangle, and so on. 1/4, 1/5, 1/6, etc. Alright, let's add our infinite series term by term and keep track of the finite sums by coloring things in orange at the bottom. Here we go. 1, color in, plus 1/2. Okay. Now, minus 1. What are we supposed to do with this? Easy. Gray out the 1 square again. Plus 1/3, and so on. Let's just keep going for a bit to get a feel for how this sum evolves. Mainly focus on what happens at the bottom, okay? Well, can you see it? There's definitely a pattern there, right? Let me highlight this pattern for you. Just watch. Okay, here it comes. One white. Okay. Okay, you know what the pattern is, right? And so the pattern is 1 white starting at 1, 2 white starting at 2, 3 white starting at 3, 4 white, and so on. Very nice. And now let's figure out the areas of these snakes of rectangles. Get ready. This is about to get really beautiful, promise. Let's go back to 2 white and let's empty the square and make the orange rectangles partly transparent. Now, move the orange snake into the square. Squeeze the snake horizontally by a factor of 2. The resulting orange area has half the area of the snake. To compensate, let's expand vertically by a factor of 2. So same area as our snake, and I hope you all had a little of an aha moment just now. We also get a perfect fit along 1 over x. Coincidence? Well, let's see. Let's do the same with our 3-unit white snake. Move in, squish by a factor of 3, and expand by the same factor. Because we're squishing and stretching by the same factor, we again get the same area as the snake. In addition, we again get a perfect fit along 1 over x. One more. Okay, on autopilot, don't do anything here, it's all pre-programmed. Then 5 white gives this, 6, 7, and so, pushing things to infinity, we get this. Great. And so the orange area between 1 and 2 under the curve is equal to the sum we're after. And then some baby integral tells us that the orange area is equal to that special number, the natural logarithm of 2. What a spectacularly beautiful resolution of this pretty maths paradox. Don't you agree? What's next? What are some natural questions to ask at this point? Well, the imbalance in the distribution of plus and minus terms did result in a non-zero sum. What if we change the distribution, for example, like this? 3 positive terms followed by 1 negative term. Or like this, 3 positive and 2 negative. What sort of sums do we get this way? That's a fairly natural question to ask, right? Here's another one. Given an arbitrary number like pi, does one of these nice distributions of positive and negative terms result in the sum being exactly equal to pi? So what I'll do in the second part of this video is answer these and a few related questions, mainly using my new skills as a rectangle snake charmer. Yes, I know. Some of you out there are yelling, Riemann rearrangement theorem. We'll get there too at the end. This and a lot more mathematical delights to look forward to, promise. 3 positive, 1 negative. 3 positive, 1 negative forever and ever after. What's the sum of that? Well, there's also a nice pattern of snakes for this one. Let me quickly show you. So here, instead of 1, 2, 3, 4, the pattern is 2, 4, 6, 8. To visually calculate our new sum, we first note that the 2 white snake fits into this box. Okay, now let's squish and stretch the 4 white snake into the box. Move, squish and stretch both by a factor of 2, squish and stretch. Remember, same area as the snake because we squished and stretched by the same factor, and a perfect fit along 1 over x. Looks like this pans out exactly like before, but better be safe than sorry, and so let's also check that this works out for the 6-unit white snake. Okay, all on autopilot again. Oh, very nice. I can just look at it. Fits again. If we keep doing this, we end up with our new squish and stretched snakes filling in the area under the curve between 1 and 3. And again, baby calculus tells us that the sum that we're chasing here is equal to another special number, the natural logarithm of 3. Nice. And why stop here? Looks like we just stumbled across a new super pattern, right? 3 positive terms alternating with 1 negative term results in a sum of ln of 3. Replace the 3 by a 2 and we get our first sum ln of 2. And if we go for 1 positive term instead of 2 positive terms, what do you think we get for that sum? ln of 1, of course. And that makes sense. Here we've got a perfectly balanced sum in which a plus term is immediately followed and cancelled out by the corresponding minus term. And so this balanced sum is clearly equal to 0. And of course, ln of 1 really is equal to 0. Nice. Now all this generalizes in the obvious way for positive integers, like this. And even for nice regular patterns where m red positive terms alternate with n blue negative terms, we can figure out the exact sum. This sum ends up being a difference of two logarithms, there. And of course this difference of logarithms can also be expressed like this. Wonderful. Challenge for the keen among you: identify the details that are glossed over in these visual proofs. There were quite a few. And fill in those details in the comments. Now, how about we really want a specific sum, like for example pi? Can we arrange for m and n to be such that the sum becomes pi? Obviously, the most life and death question of the century, right? Well, let's see. So we want this to be equal to pi. Well, let's solve for m over n on Algebra Autopilot. Okay, is this possible? Well, that's the same as asking whether the number e to the pi can be written as a fraction, whether this number is a rational number. What do you think? Is our mystery number e to the pi rational or irrational? Okay, here's a fun related question. Have a look at these simple ways of combining e and pi. Among these numbers, only our e to the pi has a name. Why do you think that is? Well, pretty much anybody who knows anything would bet that all these numbers are irrational. However, only for e to the pi do we actually know a proof that this really is the case. And that's why it has a name. E to the pi is called Gelfond's number, named after the mathematician Alexander Gelfond, who came up with this irrationality proof in 1934. Anyway, we can be sure that Gelfond's e to the pi is irrational, and so we can also be sure that none of our nice series sums to exactly pi. Well, bit disappointing, but not all is lost. Turns out we can get a sum that is arbitrarily close to pi. How? Well, in decimals, Gelfond's number is 20, what? 3.14. Why is there another pi here? Amazing. Actually, not amazing again. Just another one of those freak coincidences. Did I manage to trick you again into believing that there is something of significance there? Anyway, 23.14 and so on, that's approximately equal to the fraction 2314 divided by 100. Logging this fraction, we get this. All right. What this means is that if we keep alternating 2314 positive terms with 100 negative terms, the resulting sum will be the approximation of pi on the right, which coincides with pi in its first 5 digits. Not bad. And if we use more digits of Gelfond's number to build our fraction, we get better approximations. For example, there, 7 correct digits instead of 5. Nice. Okay, so those nice m positive and negative patterns don't ever get us exactly pi, but we can get arbitrarily close. And the same is true for any target number other than pi, right? Using our bag of tricks, we can find one of our nice series that either hits the target number exactly or gets arbitrarily close. Cool. Now, remember, in all the infinite series that we're considering here, we are always using the same terms, 1 minus 1, 1/2 minus 1/2, that cancel each other out in pairs. And so our initial a minus a not equal to 0 paradox just got a little bit more paradoxical in that we can force a minus a to be equal to pretty much any number we like. Still, pretty much any number is still not every number. So, what's our next question? Well, obviously, can we hit every number we like exactly by also using series that are not so nice? Can we? Well, actually, yes, we can. Let me also quickly show you how that works. This is something really very important that everybody interested in maths should know about. Let's start by having another look at this fact. M positive terms taking turns with one negative term gives the sum of ln of m. I claim that this implies that the sum of the positive terms alone explodes to infinity. Why is that? Pretty obvious, right? As we let m go to infinity, so does the sum, the natural logarithm of m. And of course, the only way we can push the sum to positive infinity is if the positive terms, just ignoring the negative terms, add to infinity in the first place. Easy. Okay, Now let me show you how this implies that we can arrange the positive and negative terms to get a sum that is exactly equal to pi. All right? For this, let's first list all our positive and negative terms. There, all the positive terms at the top and all the negative terms at the bottom. Now let's roll in the number line. I've already highlighted our target number pi, and we'll keep track of our sum using this arrow. Okay, here's the idea. We'll start adding positive terms until our sum is greater than pi. There, 1, record this on the number line, plus 1/2, that's 1.5. Now keep adding positive terms until our sum exceeds pi. Okay, adding. This happens after we've added 1/13, and now we are left with these positive terms. Then we add negative terms until we are below pi. Actually, just adding that -1 will get us below pi. Update what's left in terms of negative terms. Then we keep going with our positive terms until the sum is greater than pi again. Okay, so there we go. Okay, switch back to using negative numbers. Add negative terms until we're just below pi, and then keep on alternating between using the positive and negative terms forever and ever after. And in this way, we end up with a sum that is exactly equal to pi. There, exactly equal to pi. The pi lover in me is happy now. Why does this work? Well, on every step, we're either overshooting or undershooting pi, right? This means this process continues forever. Now, since we are forever switching back and forth between using positive and negative terms, eventually every term will be used. And since the terms are petering out to 0, we'll be over and undershooting less and less. This means that the finite sums will be converging to pi, and that therefore our sum is pi. So simple, so cool. And of course, there was nothing special about pi as a target number. The same procedure will work for any target number whatsoever. You want the sum to be equal to 666? Not a problem at all. Not bad, huh? Okay, and this then completes our paradoxical mission. Using this over and undershooting algorithm, we can arrange our cancelling terms to give any sum whatsoever. Fantastic. But there's more. There's a super important way to rephrase and generalize our paradox called the Riemann rearrangement theorem. Let's finish with that. Start with any of the series made up from our terms over there. For example, this alternating one here. When you are dealing with finitely many numbers, no matter how you rearrange those numbers and no matter how you add them up, the sum will never change, right? Take the numbers 1, 2, 3. Then 1 plus 2 plus 3 is the same no matter how you arrange these numbers. 1 plus 2 is 3, plus 3 is 6. 3 plus 1 is 4, plus 2 is 6, and so on. The sum is always 6. However, as we've seen, this is no longer necessarily true for infinitely many terms. Arranged in this series up there, the sum of the infinitely many terms is 0. However, as we've seen, this infinite series can be rearranged, creating a new series with any desired target sum. I still remember being very surprised by this counterintuitive result the first time I came across it. And this is also something you always have to be wary of when manipulating infinite series. Okay, let's say you're one of those chosen infinite series manipulators, and let's say somebody challenges you with a mystery infinite series. How can you tell whether this series can be rearranged to give different sums? Easy. Split the series into its positive and negative parts. Then, what made the over-undershooting rearrangement algorithm work was this. First, the fact that both the positive and negative sums are infinite. And second, the fact that both the positive and negative terms peter out to 0, right? We didn't use anything else to guarantee that our algorithm spits out a series that adds to pi. So as long as we have an infinite series whose positive and negative parts have those two properties, we can rearrange the series to get any desired sum. A series like this is called conditionally convergent. On the other hand, it is also fairly easy to see that all other series either have no sum at all or have sums that don't change when you rearrange the terms. For example, the alternating harmonic series that we started with has these positive and negative parts. 1, 1/3, 1/5, etc. Those are the positive terms, and minus 1/2, minus 1/4, minus 1/6, etc. Those are the negative ones. Clearly, both the positive and negative terms peter out to 0, and it's also not hard to check that the sum of the positive terms is infinite, as is the sum of the negative terms. This means that the alternating harmonic series is conditionally convergent. It can be rearranged into series that give any sum whatsoever. I already mentioned this in this other video here. You may be familiar with that. Anyway, that's pretty much it for today. Well, one more thing. While I was playing around with my snakes, I also noticed that I can use some really weird snakes to figure out the exact sums of the nice m-positive and negative rearrangements of the alternating harmonic series. Let me finish off by giving you a taste of this in an animation accompanied by some funky music. And that's it then for today. Well, actually, I still have to say a little bit before I can hand over to my algebra autopilot. So what I'll do is start with the alternating harmonic series and rearrange according to the pattern 2 positive, 1 negative, 2 positive, 1 negative, and so on. There, 2 positive, 1 negative. As we did at the beginning of this video, we substitute all the negative even denominator terms by those difference in brackets, remember? And now, as usual, we go snake hunting in the 1/x jungle to find out what the sum of this new series is. And here is the pattern that we spot.